Let's talk about constant acceleration problems. This is a little different from how you originally see position, velocity, and acceleration. The basic equations are the same, that the derivative of position, which is usually called s, is velocity. The derivative of velocity is acceleration, and therefore we can sort of shortcut that if we want to sometimes. The second derivative of position is acceleration. That, if you start with position and then go to velocity and then go to the acceleration, that's about derivatives. But often the more interesting problem is to go from acceleration information to position information. And we really want to relate all three of those sort of up and down the ladder. And you can do that, and so that's antiderivatives is a really important thing. The assumption here for this video is going to be A is just a constant, and that simplifies things tremendously and gives us just sort of one set of master formulas. So let's do that. Let's look what the master formulas would be. If A is a constant and V is the antiderivative of A, so V prime of t is just a number A, then V of t, well, constant just anti-differentiates to constant times t. Remember, t is the variable here, not x. But then plus an arbitrary constant. You always have to add in that arbitrary constant. Now, the annoying thing, though, is that mathematicians are probably fine with that, but a physicist wants us to say, well, what's the meaning of c? What's the physical significance of that? And the easiest way for that is if you happen to know the velocity at time 0. And we're always going to assume that. And often we can assume that because we get to set what time t equals 0 means. It's usually just the start of our experiment. And so v of 0 is just going to be, oh, hey, this dies, at dies, and that's just going to be c. So guess what? We don't have to use some sort of generic notation c. It really has a meaning. And in fact, we actually usually just abbreviate this to v naught, v sub 0. And so it's going to be at plus v sub 0. So that's going to be one of our fundamental equations. It's a very simple equation. Under constant acceleration, the velocity is a linear function of t, starting with some starting. That's our intercept value for the straight line, and the slope of the straight line is a. Okay, now we can continue. We know that s prime of t is v, and now we know what that is, at plus v naught. So s of t, let's see, constant times t, that's going to turn into 1/2 t squared times a, so in other words, 1/2 at squared. Remember, when you've got a t to the 1, let me emphasize that, whatever this power is, you increase it by 1, and then you just put this out in the denominator to cancel it out. So when you take the derivative, they'll cancel and you get back to here. The only exception, of course, is if that power is -1, in which case you get a natural log. It's very different. Now plus antiderivative of a constant again. Okay, so just v naught t. But then don't forget we need another constant. Every time you anti-differentiate, not just once per problem, it's every time you anti-differentiate. Because if you take the derivative of this, the c will definitely die. You'll definitely get this. And again, we want the meaning of that. Well, once again, let's just plug in t equals 0. We'll call that s naught. And then conveniently, this stuff dies. Usually, for a more complicated anti-differentiation problem, this stuff doesn't die. And it's not just the constant is the value of the function at 0. In this case, both of these cases where if you see, it happens to be true. So we finally get our summary, 1/2 at squared plus v naught t plus s naught, the starting position. And I'm going to actually break that out. I'm going to just display that and this one together because those are the punchlines. Both of those are useful. Two equations about position and velocity. So those are our master equations. They might be familiar from a physics class, and often they're derived without calculus, or they just tell you, trust us, they're true. But here you can see what's really much the most elegant derivation of that using calculus. Okay, so let's do an example. A car accelerates from a standstill to 90 kilometers per hour over a distance of 400 meters. What was its acceleration, and how long did it take to cover that distance? So what usually confuses people about these problems is not the master formulas so much as just how do I start it? How do I set it up? And that's true of any physics problem. That's the hard part usually. And the nice thing here is that even though the problems often look different from each other, they all fit into a standard pattern. There's a standard template for these problems, which is that there's 6 quantities of interest, and they're almost always going to give you 4 of them. Although some of them you might have to figure out how they're giving you in words instead of numbers. Our standard template is that the 6 quantities are the initial position, the initial velocity, of course the acceleration, which is assumed to be a number, a constant, the time this all takes, and then a physicist would often call these two guys like S final or V final. In the book it's usually what's the position after a certain lapse of time, whatever this mystery time that the whole process takes, and what's the velocity after that time. Okay, so this is like, it'd be more parallel if we actually use the notation S of 0 and V of 0, and that's the initial, and then S at the final time t, V at the final time t. And what's going to happen is that some of these are going to be unknown, and 4 of them, hopefully, if you're going to be able to solve the problem, are known. Let's do this example in that spirit. From a standstill, that's telling us that the initial velocity is 0. And of course we're assuming that the time at the start of what's happening is 0, and that's a very standard assumption that very rarely would you have to mess with. The acceleration is clearly unknown. The time is unknown. Those are both asked for. What about the initial position? Well, that's something that you can usually choose. Very, very often you're just going to choose that to be 0. Now, there's going to be problems where it's more natural to say S of t is 0. So, for example, if a rock falls off a cliff and then thud lands on the ground, you might well want to say the final position is 0, and then the height of the cliff would go here, whether it's known or unknown. So that there's definitely cases where this is not 0. But here, there's no reason not to say, okay, we're going to put our tape measure, the end of our tape measure, at the place where it started. And then that tells us what S of t is. Because it was 400 meters from where it started to where it got to 90 kilometers an hour, this is going to be 400. Okay, so that's the other issue, is that one of these quantities, usually either one of this or this, is something you can actually just set by fiat to be something simple, usually 0. And then V of t, that's the ending velocity. Oh my goodness. Now I bolded these to make sure I remember and talk about this. Kilometers per hour, meters. Ooh, kilometers, meters is a unit mismatch. And also, hours, probably not very reasonable. If you think about this, that's like highway speed. That's, the length of a track. We're not talking about hours and hours to do this. It's probably going to be seconds to do this. And so we probably want to convert this to meters per second. Okay, so let's say that's equal to, well, let's just do it a little displayed here. 90 kilometers per hour is 90 kilometers per hour times, we're just going to multiply it by 1 repeatedly, 1,000 meters per kilometer, but also 1 hour is 3,600 seconds. We've multiplied it by 1, multiplied it by 1 again. Meters, the kilometers will cancel, the hours will cancel, and you get 90,000 divided by 3,600 meters per second. Okay. Ooh, it thinks that's secant. That's why it's in a different font or a different color. And then we can simplify that. Take 2 zeros out of both. Factor of 9. And that's just 25. So in fact, it's 25 meters per second. Okay. So we really want to write that as 25 meters per second. Okay, so they're going to put 25 here. Now everything's in meters and seconds, and that's how the answer is going to come out. Okay, so we got our standard template. Now we just bring down our equations and see what happens. Oh, stop that. I know that can't be necessary. Okay. Alrighty, so we're just going to plug everything in. Let's do the second one. This one is often the one to start with because it's easier. 25 equals, well, a and t are both unknown, and v naught is known to be 0, so it's just at. Often, one of these equations, very often the second one here, the velocity equation, will only have one unknown, and you'll just be able to solve it right away as soon as you write it down. Here, I chose one on purpose that you actually end up having to solve a system. But it's not going to be that bad. Okay, now s of t, that's 400, that's the total distance, is 1/2 at squared. And so in general, you'd have this kind of stuff. And the most complicated of these guys is where you have to solve for t and it ends up being a quadratic. And maybe I'll do that in another example. But I think this is kind of a cool one. Okay, so I have to solve this system. You could just go ahead and solve for a or solve for t up here and plug in. But there's a better way to do it, just to recognize the similarity between the right-hand sides. Hey, this right-hand side is at times t. But I know what AT is. It's 25. And so I get 25 over 2 times t. Okay, I can solve that. So t is just 2 times 400 over 25. And that is equal to 32. So in fact, it takes 32 seconds. So I'm going to put in the units. 32 seconds. And then A is easy. It's just 25 over t. Oops. A equals 25 over t equals 25 over 32. And what is that? Let's see. The 25 was meters per second, remember? Meters per second squared, because this is the 25 was meters per second and the 32 had another second. And that's definitely the right units for acceleration. Distance per time squared. Okay. So that's an example of how those how that template works for this kind of problem.